So up to this point, we've talked about big O notation, big omega notation, and we've talked about big theta notation. We've seen some examples. I'm now going to talk about little o, which is another asymptotic notation. So let's define this together. So it's written usually with a lowercase o, not to be used with a capital O or a 0. So we say f, so if I give you two complexity functions, f and g, we say f is little o of g, if and only f. So I must stress that whatever's here, if this is true, whatever's going to follow after the if and only if will also be true. If this is false, then whatever comes after the if and only if also has to be false. If and only if f is big O of g, and f is not big theta of g. So you might be looking at this definition. So let me just reiterate. So f is big O, f is little o of g, if and only if f is big O of g, and f is not big theta of g. So just to be clear what that means. So you already know that big theta is an asymptotically tight notation, right? Big O is an asymptotic upper bound. So if I want to use an analogy to explain this to you, if you know that big O is an asymptotic upper bound, you can think of that in terms of the inequalities. You find a C, you find an N0, and you show that F is less than or equal to C times G of N, correct? So this operates like, well, I like to think of it like less than or equals in terms of asymptotic growth of order. So it's like, so if I give you like a constant function versus a linear function, you could say the constant function is big O of the linear function, correct? But you can't do that with big theta, right? Big theta is an asymptotically tight notation, and it operates like an equal sign. So if it's saying that it's not big theta, that means it's not going to be asymptotically tight. Instead, that means, as a result, that it has to be strict. So what do I mean by this? So let me give you an idea what I mean. So the way little o notation gets used, is you can think of it as a, I like to call it and say it's a strict asymptotic upper bound. So for example, you can say that 1 is little o of n. You can also say something like log base 2 of n is little o of n. You can say, for example, that n is little o of n. But you, actually, can you say that? No, let's make it n squared. But if you were to say that n is little o of n, if you claim this, does that make any sense given this definition? No, not really. Because sure, n is big O of n. That's not very hard to prove using the definition of big O. However, what's wrong with the n being a little o of n with this definition? Is that it's not allowed to be asymptotically tight to whatever's in the notation, right? So it can't be that, because remember, if I've established this, that means that what it's really saying is that it's not big omega of whatever that is. So it can't meet the asymptotic lower bound. It's strictly bounded from above when it comes to asymptotic orders here. So you can't say that n is little o of n. It's because it fails the second condition here. And one thing I need to mention, as just a sideline into this, is that when it says, since we know that f is big O of g, and that means that when I say f is not big theta of g, that really is me saying that f is not big omega of g. Do you see that? So this is going to come up now with our alternative definition for this. So this is an equivalent second definition. So I'm going to give you a second definition. There's a second definition. It's going to take the logic that's underlying this and put it together. So we can say that f is O of g if and only if for every for every positive real constant, C, there exists an n0 that's a positive integer such that f of n is less than, it's just strictly less than, c times g of n for all n greater or equal to n0. So this is the alternative definition. This should remind you of the big O definition. It just has some small tweaks to it. The first one is that you're not picking C anymore. C is arbitrary now. What you're picking in this definition is n0. So there's only one constant you have to worry about in this definition. It's just n0. You might ask, Dan, where did this come from? So, well, then the fact that inequality changed a little bit. So remember what I said. You have to prove that it's big O of the thing. So f is big O of g. So you can see that there's elements of that in here, right? So remember, if you were to show me this worked for every positive real constant, that definitely covers there being a positive real constant, right? So yes, that's in here. We find that there exists this positive integer. And it has to be that most certainly f is less than, f of n is less than c times g of n for all of these, right? Like a lot of this seems similar. The inequality is sharp now as opposed to it being less than or equals. Now you might ask, okay, so why does it say for all c? Well, let's think back to when we're showing that something is not big O of another thing. Well, the argument is very similar for big omega. So what does this mean? If I know this is true, what it's really saying is that f is not big omega of g. So how would the game plan work in this? If it was big O, what would you do? Well, the direct negation of this statement would be that for all, so it has to be for all c and n0, right? It has to be for all of these. So c is a positive real number, n0 being a positive integer. There is n greater or equal to n0 so that, and remember in the big omega definition, it's that f of n is greater than or equal to c times g of n, correct? So if I negate that, that means that f of n has to be strictly bigger than c. Sorry, not strictly bigger. It is not strictly bigger, right? Remember, it's greater or equal for the original definition, so it means it flips like this. It's strictly less than c times g of n. So what you do is you take these two things, you lump them together, you get this. So you take the logic that entwines both of those conditions, you get this. That's where actually this comes from. So if you're wondering why this is the way it is, it's actually because you combine the underlying logic of these two statements. So if this is the case and this is the case, you get that. So you basically drop out the stuff that just doesn't work between both of them. So hopefully this gives you some appreciation for this definition instead of that one, but I'm going to show you how you might use these, okay? I thought it would be a good idea we kind of try doing this with a fairly easy example, but do it in a way that is still in the theme of what we're talking about. So I thought the first thing we'll try throwing the little o notation at is, and we're going to use the second definition, and then I'll use the first one for another example, okay? So the first claim that we're going to try showing is that 0 is little o of 1. That's what we're going to try proving first. So remember, the way we defined our complexity functions is we allow it to take on the value of 0. We'll have more discussion about this later. So anyways, we're going to try showing that 0 is little o of 1. So we're going to use that second definition. So remember, that one says that for every positive real constant, for any one that you pick, there's going to be, and keep in mind, you don't get the choice of it. It has to work for any one. there exists an n0 such that you get the sharp inequality here of f of n is strictly less than c times g of n. And it has to be true for all n greater or equal to n0. So here we go. So let us prove the claim using the second definition. Using the second definition. I must stress that these definitions are equivalent to each other. There's nothing you can lose in between. It's just the way that you would go about proving it. The structure of it just changes a little bit. This sort of cuts out all of the other stuff, all the fluff. So, for any c, which is a positive real number, we find n0, which I must stress this is a positive integer, such that for all n greater or equal to n0, 0 is going to be less than or equal to c times 1. This is going to remind you of another example we did. And it's not a coincidence either. So, anyways. Well, what's the first thing you know about c? C is strictly bigger than 0, right? Well, c is strictly bigger than 0. So notice that regardless of n, so no matter what value n takes on in this function, the inequality is true. The inequality holds. So I'm just going to choose n0 to be 1. Therefore, so now I've done everything I need to do. Therefore, by the definition of little o, 0 is little o of 1. And that concludes the proof. So a couple of tips. So the first one is just remember the game plan. You don't have control over C. C is arbitrary. So you're going to imagine it like somebody gives you C in this claim. So I don't know what C is, but there's a big perk that we get out of having that, is that when I give you C, I'm allowed to pick N0 and I'm allowed to use C. So sometimes when you're proving claims involving little o, it'll be the case that when you pick N0, it might have a relationship with C. So if I give you a C, then I can show you how to get N0. So that's a tip I can give you about proving little o claims. So beyond that, you're going to find a lot of the strategies we've used in the past for big O will generally be helpful here. But the point is that we need to make sure we pick that constant big enough that will satisfy it in this case. So actually, I'm just staring at this a little bit. I noticed that actually I wrote less than or equals. This is sort of my mental memory going on here. So it should be that it's less than like this, right? I didn't have anybody to correct me, so I'm just going to fix it there. So either way, our argument still works, right? That's what I was saying. It wasn't a coincidence. So hopefully this argument makes sense for everybody. So just remember, it's a strict inequality there. But yeah, so that's how we can prove 0 is big O of 1. Not big O of 1, it's little o of 1. Because we already, by the way, if you're curious, if you haven't tried or seen this, yeah, you can prove that 0 is big O of 1. So anyways, what we're going to do next is I'm going to now show you how you can show that something is not little o of another thing, okay? So now that we've seen that 0 is little o of 1, Let's show that, that there actually are functions that aren't little o of a something. So you're going to find that the first definition that I gave you is actually going to be a bit helpful when you want to accomplish this. So remember, in the first definition, I'm just going to keep up these conditions here. So the next example we're going to do is actually going to be proving an is not claim. So as opposed to an is claim like we just did. So previously we've shown that 0 is little o of 1. I'm going to now show in our next example that a constant like 2022, I just thought because it's current year and all, that this is not little o of 1. We're going to try proving this. So the reason why I like to show at least a couple of ways you can define little o is that when you think of this simpler one where you have f is big O of g and f is not big theta of g, what does it mean for this not to be true? So remember, this means that both of these are satisfied. So what does it mean for this to be not true? So if I number these 1 and 2, so if I want to satisfy the little o definition, it has to be that it satisfies both 1 and 2. For it to be not true, what does it mean? It means that one of 1 or 2, so 1 of 1 or 2 fails. So it gives you a recipe for quickly proving that something is not little o of a something. So here we go. So what I'm going to do is I'm going to negate the definition. So negate the first definition that I gave you, but I'll just call it the definition because that was the first one I gave you. Then we can show at least one of 2022 is big O of 1 and 2022 is not big theta of 1 is false. Remember, that's our game plan. So this is our game plan here. So I have a question for you. Which one is the better strategy here? So which one of these should we tackle? Well, I can first tell you, and I want you to convince yourself of this, is that 2022 is in fact big O of 1. So this is actually a true statement. That's true. So which one is the culprit if this is what we're trying to prove up here? It's this one right here. So if you wanted to refute this claim, what would you do? So if you want to show that this is false, what are you actually trying to do? You're trying to show that 2022 is big theta of 1. That's what you do. So I'll say, it is true that 2022 is big O of 1. So to prove the claim, we show that 2022 is big theta of 1. But what part is missing? I already know that's true, right? And keep in mind, if you're not convinced by this, and if you want to exhaust out this proof, I encourage you to do that. Do this part of the proof. So we show this. Since 2022 is big O of 1, what remains is to prove that 2022 is big omega of 1. So if we can prove that, then we're done. Does everybody see that? So that's all we got to do. I'm going to try a different marker. So now all I got to do is prove that 2022 is big omega of 1. We find constants. We find constants c, which c is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, I'm just going to switch my marker again. I keep switching markers. This one's starting to act a little funky, so I'm going to switch to a different marker. Let's try a different one. Such that for all n greater or equal to n0, it has to be the 2022 is greater or equal to c times 1. So this is surprisingly easy for us to approach if you understand what we just wrote down. So I picked those two constants such that 2022 is greater or equal to c times 1. What's a natural lower bound here? If I pick c is equal to 1, right, then I have 2022 is greater or equal to 2000, well, it's greater or equal to 1, right? That has to be true. If you really don't like that, you can always set c to be 2022, then they're equal to each other. But the point is there's a lot of flexibility for how you pick this constant. So I'm just going to pick c is equal to 1. Then 2022 is greater or equal to 1, which is true for all n greater or equal to 1. So select n0 is equal to 1. So now we got our two constants. We have something to check that. We have an argument for that. Therefore, so now we can put this all together now. Therefore, by the definition of big omega, 2022 is big omega of 1. And as a consequence of the argument we have above, and as a consequence, that says consequence over there, it sort of melted in the microwave a little bit. And as a consequence, what does that mean? It means 2022 is not little o of 1. And that completes the proof. So I thought I'll give you some examples of how we can use little o in some basic examples. So if you thought that was kind of neat. So notice that little o, I find, is a little easier to manage if you understand that it's really comprised of these two parts.